Hey guys, we're going to go over the multiple choice problems. So your homework was or is 1 through 7, 9 through 21, and multiple choice 23 through 28. So let's take a look. It says you read in a book about bridge that the probability of each of the four players is dealt exactly one ace is approximately 0.11. So thinking of the table here, right, you're playing bridge with four people. They're talking about each person having an ace in their hand, everyone having an ace. So if you think about it that way, that's that would be not very likely, and so that's why it would happen, let's say 11% of the time, if you played the game many times, right? And so now we're looking for the words that mimic the script that we establish in class. So this one says, in every 100 games, you'd get exactly 11. No, I mean, essentially you'd get it about 11 times for every 100. So we don't like A. B says, in 1 million bridge deals, the number of deals with which a player would have one ace would be exactly. Again, no. It would be about, it would be somewhere around. We wouldn't be surprised if it was very close to. Any of those is appropriate, but exactly is not appropriate. So looking at C, it says in a very large number of bridge deals. I like it. This is like our script. The percent of the deals of which each player would have one ace would be very close to 11%. This matches what we're looking for. So let's look, though. In a very large number of bridge deals, the average number of aces would be close to that. This is saying something different altogether. This is, and the average number of aces you would ever get could be like a decimal of some sort. So, because remember, think, you could have 2 aces in your hand, 3 aces, 4 aces, or no aces. So they switched kind of what we're talking about there. E says if each player gets an ace in only the first 2 deals, then each player should get an ace in more than 11%. And this we know is wrong. The chances of this happening is the same every single time we play bridge. Every single time we play, every single time we deal a hand, it's exactly the same and it doesn't change. Okay, 24. If I toss a fair coin 5 times, right? Toss a fair coin 5 times, and the outcomes are tails, right? Then the probability of tails appearing on that next toss, once again, we know these are independent events, so it shouldn't change. It should be the same each time, which is the reason why I didn't pick E. That's kind of where they were leading me down path there. All right, now for exercise 25 through 27, we're referring to the same setting. So kind of like what we did in class, where my free throw percentage, I think, was around 75%, depending on the class, right? A basketball player claims they have a 47% shot from the field. We want to simulate the player taking a set of 10 shots. Okay, so they take a set of 10 shots. So it's a shot. 10 shots were taken. And we could miss them all, make them all, or some combination between there. What would, assuming that our claim is true, how would we go about simulating this? Okay, so to simulate the number of makes in 10 shots, you'd perform a simulation as follows. Use 10 random 1-digit numbers, where 0, 1, 2, 3, and 4 would be a make, and 5, 6, 7, 8, and 9 would be a miss. This would be a great way to set up the simulation if her shot ratio was 50%, but it's not. It's 47. Now we look here at use 10 random digits, where 0 to 46 would be a make. Okay, so that sounds right. Because we think about it, the number 00 is a number, if it's a 2-digit number, right? And then the number 01 till the number 46 would be 46 numbers. So this would be a total of 47 numbers, right? And so 47 numbers, we're saying is a mess and is a make, and that matches what we're trying to simulate. And this would be the remaining numbers are a miss, and that's exactly what we want to simulate. So this one is the correct answer. So let's see what's wrong with the other ones. Yeah, in C, they're including this 0, 0. So this technically would be 48 numbers. So this would be a correct simulation if her shot ratio was 48%. In D, it's having us use 47 random digits, and that's not, we needed to do a trial of 10. We need a trial of 10. So that doesn't work. And then for the same reason, we need a trial of 10. And so they're kind of mucking that up there, trying to confuse you. All right, same scenario, and they did similar to what we did in class here. So it says a total of 25 trials. So there's 25 dots here. And each one was a simulation, so you could think of that as each student. There were 25 students in class, ran the simulation, and a set of 10 shots taken. So this would be a student who ran a simulation whereby they took 10 shots and 7 of the 10 were made in that single simulation. All right, so now that we know what the table means, it says what would be the approximate probability that a 47% shooter, so these were simulations made from that basis, made 5 or more. So we essentially need to count 5 or more. And so it looks like there's 9 here, right? 9, 10, 11, 12. So 12 people in the simulation out of a total of 25 made 5 or more. So if we look at our choices, that is in fact one of our choices. So we select it as our answer. Now, using the same setting, suppose this player attempts 10 shots in a game and makes only 3 of them. So we go back to our simulation, makes only 3. Okay, let's see. What would be an approximation of the chances of making only 3 if, in fact, we're presuming that the shot ratio really is 47%? So when a simulation did presume that the shots were made at a 47% of the time, notice we ended up getting 3 or less, 4 out of the 25. Interesting, right? So we really need a quick calculator to decide, well, what would that be? So that would be 4 out of 25 is 0.16. So although it's not a huge likelihood, it is rather likely, 16. And our threshold for that is like 5% or less, right? So we need to say, does this provide convincing evidence that she's something less than 47? And our answer here's got to be no, right? So no, and I believe it's C, right? It is plausible that she would make 3. 16% of the time is rather plausible. I think we're okay with it repeating 25 times. It's more than half. Yeah, all of those are wrong. So let's see, what would the yeses mean? It says yes because 30% is less. This would be absolutely not. Anytime you're using the numbers in that way, you're not mimicking what we're doing in class. All right, B says yes because she never made 47%. Well, we know she's never going to make, it's actually pretty unlikely if she played all these games to make exactly 47%. That's what she would make in the long run. And she wouldn't even maybe make that. She'd make something close to that based on variability. Now here we come to the final question. It says 10% of the U.S. household contains 5 or more people. So this is what this would maybe look like. So it maybe help you kind of picture what they're talking about. Okay, so if you live by yourself, you'd fall there, right? So here's maybe the U.S. population. And they're saying, if I collected a bunch of data, 10% of the time, so that you are 5 or more. So they're saying that 10% of the time, you would have 5 or more. If we were going to simulate this, how might we do that? By recording a yes if it contains 5 or more. So this one, if we said odd is a yes and even is a no, that would happen 50% of the time, and we're looking for 10. This one, we have 1 0, right? And there's 9 of these, right? So that would mean 1 yes out of a total of 10 no. That's 10%. So I like this one. Let's calculate what's wrong, though, with the other ones. So this is 6 numbers, 1 through 5, and the number 0. So that would happen 60% of the time. You'd get a yes. Here, this would happen 1 through 4, and then the 0. So this would also be a way to simulate something we're trying to simulate that happens 50% of the time. So we've chosen our final answer, B. Thanks for joining us, guys.